So our job today is to extend our formalism into constraints and a few other things. But the first job is introducing constraints, and I'm going to try to supplement Goldstein's approach rather than just following it blindly. That you should still do that. Okay? I'm not saying that the things that I do is better than what Goldstein does. I'm just trying to complement it. Okay? I'm assuming you actually read the book, and you, if you had questions about that, you would actually ask them to me. But I also want to give some alternative roads because these things can be very confusing. Now we are going to be dealing with polynomial constraints. Polynomial constraints. And we already have a way to deal with them, the generalized coordinates. Right? So we can use polynomial constraints to eliminate some of our Cartesian position coordinates, and then we end up with generalized coordinate. Or I mean, then you can just write everything in terms of those. You're going to have some reduced number of equations, and you get your Lagrange equation of the second kind, and you solve them now. But this is sometimes not practical, right? Even though you have a constraint equation, sometimes you can't really use them to eliminate some of the variables. In principle, you can, but in general, you can't. I mean, you can see that, okay, this is an equation in 3 variables. I can use this to express, one of the variables in terms of the others, but sometimes it's not practical. And sometimes you want to actually calculate the constraint force. Okay? So Lagrange equations of the second kind, or simply Lagrange equations, as we call them, do not provide this facility. You cannot get the force, and you want to get the force sometimes. Okay? So this is going to be a way to get the force. And instead of going into the full derivation of this from Hamilton's principle, I first want to make a derivation related to D'Alembert's principle. Right? So let's recall. Geometric relations. So I'm going to write them slightly differently than before. Instead of small f, I'm going to use capital G, because small f I'm going to use for the constraint force. So this is going to be some function of 1 or 2 of the Cartesian position coordinates of the end particles, and this is equal to 0. So there are k of these. Because of this n particles positions, we're going to have 3n degree of freedom, and this k of k equations is going to reduce this degree of freedom from 3n to 3n minus k. And so degree of freedom goes from 3n to 3n minus k. Okay. This is something we said before. Now, I'm not going to fully use D'Alembert's principle, but D'Alembert's principle was based on a property of the constraint forces, that they do no virtual work. Okay? So I'm going to write that down as well. So this, yeah. So over all the particles, 1 to n, this is our constraint force on the ith particle. This is the virtual displacement of ith particle. This is 0, right? So this means that the constraint forces does no virtual work. This is the meaning. Okay. Now I'm going to try to manipulate these equations and try to get some equation for this fi. And there's a trick that is much easier to see in this context than to see in Hamilton. Well, for me, okay, this is something subjective, obviously, but for me, it's much easier to see it in this context than to see in Hamilton's principal context. So this is the first thing I want to do. Now, we have these virtual displacements, and these virtual displacements, remember, have to be consistent with the constraint equations, our kinematical relations, right? So what I'm going to do is I'm going to write this and make a Taylor expansion. Okay? So I'm going to write the kinematic relations with the virtual displacement and apply a Taylor expansion. Okay? So this is going to take some space. So I'm going to just call this equation 1, and this one equation 2, and erase everything because I will actually need the board. But I will simply be taking equation 1 and rewrite it. So that the initial privilege was just to provide context. Now, this is going to be R1, delta R1, R2, delta R2, Rn, delta Rn. Okay, so this is equal to 0 because our virtual displacement had to be consistent with the constraint. This is what it means that this is equal to 0. Okay. But this is also equal to some Taylor expansion. Now, how do you Taylor expand this? So let's start with this one. Okay. So I'm going to write this as GR1, no, R2 plus delta R2, Rn plus delta Rn. Okay. So this is this is something we know, plus this delta R1 dotted into the gradient with respect to the first coordinate of this function, evaluated as R1 delta R2, sorry, R2 plus delta R2, Rn plus delta Rn. It is perhaps a little bit hard to read, so let me just go. So this is the full thing with the visual displacements. Here, I'm going to one coordinate without the displacement, expanding around that point. So this gives me this dot product, right? If this was a scalar, it would just be a normal product and a partial derivative, but because it is three terms, it's going to be a dot product with the gradient. This gradient is with respect to these coordinates only. Okay? That subscript means that it's with respect to R1 only, and we're evaluating the value of the gradient at R1, R2 plus delta R2, blah, 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 Rn plus delta Rn. Okay? Plus there are higher order terms. So terms of order delta R squared, which we are going to negate, of course. Now, if you repeat this procedure, so you take this, and then you take this one, and then expand this around R2, then you're going to get the kinematic relation function for R1, R2 plus R3 plus delta R3, blah, blah, blah. And then you do this for all n Cartesian coordinates. What you end up with is going to have G R1, R2 down to Rn, and then some sum over all of these terms. They are all going to look identical now, because you also expand these guys and get rid of those. So I'm going to call it Rj dot the gradient with respect to j coordinate of this function G, and I'm going to evaluate this at R1, R2, Rn, okay, plus the higher order terms squared. And now this is also 0. Right? This is just our original constraint equation. So this is also 0. To the order of delta R. Okay, it must be equal to 0. Now I take this and I add this to the equation 2, which was saying that the constraint forces do no work. Okay, so oh, sorry, this is delta. Right? Are there other typos? If you see something funny, just tell me. Okay. I hope there aren't anymore. But these are just deltas, of course. So these are the deviations from your original point dotted into that, and so forth. Okay, if we take this and then add this to our original equation for the constraint force, then we're going to get this. And delta R5 dotted into, now there is the constraint force plus, I'm going to not just add this, but I'm going to introduce some coefficients over here. Delta I Gj. Okay. And I can do this for everything. So this one is for a particular kinematic relation. I have j of them. And I'm not going to just add those, but I'm going to introduce a coefficient in front of them. So I'm multiplying 0 by some coefficient. So it should still remain 0. I can still do this. Okay? Now, why we'll do this is I'm going to explain in a moment. But let's first try to say something about it. So this is equal to 0. Okay? And usually at this point, what I want to do is to say that, okay, these are independent. So this has to be identically 0. And so I can just write this as a separate equation. But in this stage, I cannot. I cannot because these are not independent. These are Cartesian coordinates. I have constraints. They are bound by constraints. So I cannot say that I can set all of these, all but one equal to 0 and make one very small. So for that value, for that to be small, the corresponding sum has to be 0, and this has to be correct for every little delta, right? But in this case, I cannot, because perhaps I cannot set all of these to 0 and make one of them very small. They are not independent. So what do I do? Now I have 3n of these coordinates, right? x1, x1, y1, z1, up to xn, yn, zn. Now, and I have these guys. I have j of them. Now, the first thing I do is out of my 3n coordinates, n minus k independent ones. Yeah. I'm not saying get the equations for this. I'm not saying transform to generalized coordinates. I'm just saying, use your equations and pick some independent ones. You can always do this. This can always be done. Just to give a very, very simple example, what I mean. Again, I'm going to read this. Don't need this anymore. It's just further expansion. But let's say that I have 5 coordinates. Okay? And I'm writing something like one constraint is x1 plus x2 is 3. The other constraint is 3. x3 plus x4 plus x5 is 5. Right? Very silly, but just an example. Right? So here you cannot pick x3, x4, x5 as your independent ones. They're not going to be independent. There is an equation, but you can choose one from here. You can choose x1 to be independent, and then x3 and x4. What independent by what I mean is that I can set their values arbitrarily. This is what I want. This is the property I need to say something about this equation. Right? So you can always do this, no matter how complicated these look. You can pick the coordinates. I'm not saying solve the equations. In this case, you can also solve the equations, but this could be complicated. Tangent hyperbolic, something transcendental functions, something like that. But you can always choose a set of coordinates, and the remaining ones, so you pick up k of these coordinates, the remaining 3n minus k of them are going to be independent. Okay? So use lambda j. We are going to use these. So these are just the coefficients of these coordinates, right? Or like the displacement of the coordinates. We are going to use this lambda j to make sure that the coefficients of the the dependent ones, so we chose some independent ones and some are left out. The left out ones, their coefficients will be identically 0. I can always do this because there are j equations, there are k coordinates left, and I have k coefficients here. I can always choose this to make all the coefficients identically 0. Right?
Hocam, can you explain that last part again?
Okay, so first of all, I choose 3n minus k independent ones. This we agree?
Yep. Yeah.
Okay, so I can do this. Now, there is going to be remaining k coordinates. Now, what I do is that I choose this lambda. So this is a sum over k as well. I have k constraints. I'm going to choose these lambda in such a way that the coefficient, which is this, the coefficient corresponding to the ones that I left out, the dependent ones, so to say, is going to be 0.
Oh, okay, I see. So we can just do that?
Yes, because this corresponds to k equations, and I have k unknowns. I can always solve this.
Okay, I see.
They are linear, right? So they are linear in lambda, so it can always be solved. There's always a solution. In fact, we can write a matrix and explicitly say what those are, but it's not useful because I'm not going to use that. But the idea is I can use this lambda. So this is why I introduced the lambda. I'm going to come to lambda in a second. But I introduced this lambda so I can make the remaining, the coefficient of the remaining virtual displacements to be 0 identically. I can always do this. Now, if I do that, I'm going to have a sum of over 3n minus k terms. Okay? So therefore, my markers are dying on me. We have a sum over 3n minus k independent delta Ri. Okay? So you get exactly the same expression, except the sum is not over 3n, but 3n minus k terms. And now all of these, the remaining ones, by our choice that we made over here, are independent. So I'm choosing my lambda in such a way that this is 0 for the ones that are left out, but it has to be 0 for the remaining because the remaining are independent. Okay, so this is the fine I find confusing when it comes to Hamilton's principle. So we are going to do something similar with Hamilton's principle as well.
Hocam, can we say that by doing so, we use the generalized coordinates for the system as well?
No, because I'm not actually solving the kinematic relations. So I'm not telling you what these are. These are still some Cartesian coordinates. Okay. And but they are not. They could, of course, happen to be generalized coordinates, some of them at least, but not necessarily.
Okay.
So if I was actually solving and replacing, I'm not replacing them. They're still my same old Cartesian coordinates, but I chose them in such a way that they are now independent. And the coefficient of the rest are identically 0 because I'm choosing these in such a way. Right. Now, so this one, Fi plus delta j from 1 to k, lambda j, delta I, j is 0 by choosing lambda j appropriately for left out coordinates. And this is 0 by independency of chosen coordinates. Okay. So these chosen coordinates, these chosen coordinates, and you choose them to be independent of each other, which you can always do. And we set the coefficient of the remaining ones to 0 by adjusting these guys. And because the rest are now going to be independent, their coefficients has to be 0. Okay? We can now make the argument that because this is independent, for this to be 0, the coefficient of each and every one of them has to be 0. That argument now can be done, okay, for each term in the sum. Okay, and of course, I thought this is a vector equation, but this is correct for every component. Right? So if your vector equation is 0, and every component of that equation has to be 0. All right, so we have this equation for our constraint force. Now I can reintroduce what this constraint force was. So let us recall Newton's law. Okay, so for the ith particle, what is it? So Ri double dot, the acceleration was the applied force plus the virtual force, right? This was, I think, the notation we used before, if I'm not mistaken. And this is the reason why I don't want to use small f here, right? Like this is just going to be too much. And by putting this in here, making a simple substitution, we're going to have mi ri double dot is the applied force minus, sorry, some sum over j constraints lambda j gradient dj. And even though it's not common, this is sometimes called the Lagrange equation of the first kind. We are going to call something else Lagrange equation of the first kind, something that looks like the Lagrange equation of the second kind that we already developed. But sometimes you'll see this being referred as Lagrange equation of the first kind. And this allows you to calculate, to carry out some calculations. We're going to look at this. Yeah. All right, now on to this. So are there any questions with this? So this is an alternative way to get an equation that we are going to derive from Hamilton's principle. But I think this, getting this coefficient zero business is more better motivated here. In Hamilton's principle, there are too many things happening at the same time for me, so I prefer this one. Any questions? This can still be confusing, especially if you're seeing it for the first time. This is it's not easy to grasp. Let's move on. But if you have questions, you can always ask them. I'm not receiving any emails about anything, homework, topics, or things like that. It's a little bit worrisome, but maybe I'm just repeating what you have seen before. It's possible. Now, what we want to do is to derive this from Hamilton's principle. So what we're going to do is rewrite Hamilton's principle with some lambdas, this Lagrange multipliers. So we had the action, right? So from one point to another point, or T1 to T2 if you want, LDT. We are going to take this and modify this L2, so L. We're going to sum over some constraints up to J. Let's put this over here. Okay, GJ. So the
I
way
don't
to
know if it is just me, but it's very blurry on the
Oh.
screen.
Okay. We try to find another marker.
I don't think it's the marker. I think the focus of the camera keeps changing.
I don't know how to fix it. Probably when I step in front,
Yeah, probably.
it just focuses on me. But let's try with red, some more contrast. Okay, so from 1 to 2, L plus over J, so up to J, GJ. That's why I'm trying to just move away, so the camera can focus again. But yeah, is this better to see? It's a bit of funny color, but who cares, right? Right. So, but what is this? What's this lambda? It's called the Lagrange multiplier, and it is a tool when you're dealing with the minimization problems subject to constraints. So our minimization problem, of course, the variation of this is 0. Right? This is Hamilton's principle. With some conditions imposed, of course. The variation should be fixed at the endpoints and so on and so forth. So how does this work? Now I want to give an example. So Lagrange multipliers are used in a multitude of places, and there are some nice resources on the internet. But so I picked some example that I found on the internet. I want to just redo this here, so you know what I'm talking about, how these Lagrange multipliers can be used. So we'll have a little intermission, go into Lagrange multipliers, and come back to mechanics. But I want to emphasize that Lagrange multipliers are much more common than this problem, right? Just because minimization subject to constraints is much more common than just mechanics. Right? Mechanics happens to be. Right. So, example. So I looked this up from Twitter, and I looked at a number of examples. This is, I think, this strikes a nice balance. It's complicated enough that you appreciate this is useful, but it's not so complicated that you can't actually solve it, in a few minutes. Okay. So the problem is to find the maximum of this function of two variables, a and b, which is 2a plus b minus a times b, given this constraint, a squared plus b squared is 8. Yeah. So how would you normally solve this? So you want to find the maximum of this one. If there was no constraint, what would you do?
Take the derivative, set it to 0.
Yeah. But how would you ensure that it's a maximum and not a minimum or a saddle point?
We look at the points just before and just after. So if it's decreasing, increasing, based on that. Or like
Well,
the
the
second derivative, the second
Yes.
derivative.
There is a second, which second derivative though? So with a function of single variable, there's one second derivative. You look at the second derivative, and if it's positive, then it's a minimum. If it's negative, then it's a maximum. What do you look at here? There are two derivatives for two variables, and there's a mixed derivative. And so there are 3 second derivatives. Learn this. I'm not going to tell you, but this is in standard multivariable calculus textbooks. I had to learn this in graduate school. So you're in graduate school, it's a good time to learn this. I had to learn this when I was working on a research problem. And of course, when you learn that way, you don't forget. But I'm not going to tell you, because if I tell you, you're going to forget. You're just going to nod and forget. But look this up. Okay, if you have a function, two variables, how does the second derivative works? Right. So there's this Jacobian and so on and so forth. All right, but we have this constraint over here. And one way to do that is, in fact, to get this constraint, solve it for all of the variables, substitute in, and just take the derivative and set it to 0. And so let's proceed with that one method, and you'll immediately see that how it can easily fail. So if you take this and move everything to the other side, then you get a is equal to plus or minus b squared minus 8, or 8 minus b squared. Yeah, 8 minus b squared. And then you take this and you put this in. So your f becomes 2 plus or minus 8 minus b plus b. And then this is a minus, so I multiply them. I get minus or plus. I have to be consistent here. B square root of 8 minus 8. Okay. And I look at this function and take its derivative with respect to b. I set that to 0 and I solve for this. Okay. Now, this is already formidable. This is something you can probably do, but I don't know how to do it by hand. You can do this numerically. And in fact, I did do this numerically. So I'm going to show you. So I took this function and plotted this for both branches. And this is a Gunnar-plot window. I hope you can see it. So this is for the upper one, the plus sign. This one, the turquoise color, is for the minus sign, as given by these labels here. So as you see, their maximum in both cases at 6. Okay. So this is a little bit of a weird situation that this is both the maximum, and also the function becomes undefined beyond this point. there are two other extrema, one over here, one over here. So this is at -12, this is at 4, I think, yeah. And this maximum happens at b equals about 6 or so. Okay, something like that. So no, sorry, 0.76, and this one happens at 0.75, something like that. Yeah. But the maximum is 6. That one you can read off the graph. And there are these minimas that have these nice values. Now, the way I would do this is I would use Newton-Raphson method. Okay. I don't think there's a way to do this by hand, but probably you can also just give it to a computer, some symbolic computation package, and solve it that way. But you can imagine that this could be, quite hard. For one thing, this might not be totally invertible. So here, to make this substitution, you either need to be able to invert this or turn this expression into something over there. You will still need that. You will still need that Lagrange multiplier. Don't mistake me. But it's the options available to you is a bit more when you're using Lagrange multipliers. But so this is how you will approach this one. Now the second method, the method that we are going to use, find our equations from Hamilton's principle, is by using Lagrange multipliers. So I'm going to erase this, because again, I will need some room. So the second method, method 2, is that we define a new function, function of a, b, and lambda, and we're just going to rewrite our function and introduce our constraint through the Lagrange multiplier. So this is going to be f ab plus lambda, and our constraint a squared plus b squared minus 8. So if you rewrite this, this is what was my f? 2a plus b minus ab plus lambda times a squared plus b squared minus 8. Okay, this is not a function, this is just a constant. It looks like lambda and the argument is a squared plus b squared. It's not. Right? I'm taking my constraint equation, multiplying by some constant. And I'm going to look at the variation of this with respect to my variables. I'm going to set them equal to 0 because that's what I'm looking for. Okay? So the variation of g with respect to a is 2 minus b plus 2a lambda is equal to 0. Variation of g, or the partial derivative of g with respect to b, is going to be 2 minus a. Yeah, 2 minus a plus 2b lambda. And variation of g with respect to lambda is going to be a squared plus b squared minus 8 equals 0. All of these are equal to 0. So I have these three equations for three unknowns. I'm going to solve them. Right? That's the idea. Now, this one, I actually did solve them at home. Gives you lambda equals b minus 2 over 2a. And this one gives you lambda equals a minus 2 over 2b. And these are equal to each other. So if these are equal to each other, I can set these equal to each other, right? b minus 2 over 2a is equal to a minus 2 over 2b. So the 2's in denominators cancel out. You move this b to the numerator of this one, a to the numerator of this one. This becomes b squared minus 2b. This one becomes a squared minus 2a. You add 1 to both. What you get is b minus 1 squared is a minus 1 squared. Okay. And this corresponds to b is equal to a, or b is equal to 2 minus a. So this is what I get from here. Now, take these and put them into here. Right? So this is what I meant by we have more options available. We are using the constraint equation, but I don't need to invert it. Okay, I got some result from the other equations, and I'm putting them into the constraint equation. I'm not solving the constraint equation, I'm putting them in. So this could be much harder. Of course, I mean, you're just solving 3 equations. You can do whatever you want, but there are not more paths available to you, and it turns out that there is now an easier path available to us. We will, of course, take it. Right? So if you put these in, what do we get? We get 2a squared minus 8 is equal to 0. And this gives a is plus or minus 2, and then b is plus or minus 2. This is the a equals b, this solution. Okay. So let's go to solution 1. Solution 3. This is 1. For 2, we get a squared minus 2a minus 2 equals 0. And that gives something a bit more complicated. A is equal to plus or sorry, 1 plus or minus square root of 3. And b is equal to 1 minus or plus square root of 3. Okay. Okay, so here we have 2 solutions, 2 and 2. This gives, if you put them into the function, this gives a value of 4. The other one is minus 2, minus 2. If you put them in, you get a value of minus 12. So these are the local minima that we've seen in the plot, 4 and minus 12. And both these, give 6. And so these are our maxima. And as we have seen in the plot, this actually were the maxima of that function. You could, of course, probably using mathematical or something, make a more better visualization of this. But this is how the Lagrange multipliers work. Okay? So you have a function, and you want to find some extremum of this function, subject to some constraint. Okay? So you take this function and add the constraint. So here I had one constraint, I had just one. Okay? So I could have more. I could have a number of constraints. Then I would have lambda 1, the constraint corresponding to lambda 2, multiple things, and then I would use multiple partial derivatives with respect to those. Okay, of course, with the constraint, you just get the constraint equation back. Nothing happens, but the dependency, the appearance in the other equations could be different. Okay? And then you solve those equations in some way. And as I said, the advantage of this is that you have more options available to you, that you don't need to start by inverting a very complicated function and so on and so forth. Like here, we never inverted this. Right? And in fact, I did do this at home. I didn't use a computer or anything. You can actually, yeah, this one is a bit tricky, but you have to know what you're doing and you can do it. Okay, so let's now, are there questions about this? So this is the Lagrange multiplier method for minimization of a function subject to a constraint. As I said, there are a lot of videos on YouTube. I don't watch any of them in their entirety, so I can't recommend anything particular. But there are some nice resources on the internet because it's a very, very important topic. Do not just look at the mechanics books if you want to learn this. Look at other stuff. All right, so I want to go back to Hamilton's principle, and I want to take the variation of the action, set it to 0, so find the extremum of the action, subject to some constraint. And that constraint is going to be funny. So my action is going to be like this. It's going to be modified like this. I have a number of constraints, okay, k of them, let's say, and I'll introduce them this way. The variation on this is going to be 0. This is what I want. And this is how you introduce constraints into your system. I want to find the extreme of this function. You could do this separately, but you don't have to. Now, let's do that. Let's do this variation. So this is called I. So delta I is going to be 18. Now we have a big parentheses. So first there's the variation with respect to coordinates. Dot L y, and then the variation with respect to the lambdas, the Lagrange multipliers. So this parenthesis is for that one, this one is for this one. I'm adding up over all i's. So we don't have something regarding Qij here, Qi dot here, simply because we have a whole number of constraints. Yeah, it just our relations do not depend on the velocities, just depend on the coordinates. Okay, so I'm not using R here, but I'm using Q, simply because it is possible that you eliminate some of your coordinates and move to some generalized coordinates, but you kept some constraint equations. Like there's an example in the book like that. So this could be anything. You don't need to do this all the way. You can just eliminate some of your coordinates and keep the rest, so you can find the forces or something like that. So now, again, we want to say that these are independent, and so this is going to be equal to 0 identically. And then we're going to say, by shifting the sum, we're going to say each term in the sum is going to be 0 identically. But we can't do that because these are not independent. Right. These are not independent because I have these constraints that connect them. So I cannot make the usual argument that, let's say, make all but one of these 0 and so on and so forth. So what do? I do the same thing I did before. Right? I pick up a set that is independent. I set the coefficient of the remaining ones to 0 by adjusting these lambdas. And then I say, because the rest are independent, this must be equal to 0. The coefficient must be equal to 0 for the rest of them as well. Otherwise, the integral would not be identical to 0. Right? The same thing I did for the sum that I obtained from the Lambert's principle. This is more complicated, but the idea is the same. And so how do you go from here to here? Well, you go through the steps. We did for Hamilton's principle without the constraint. So it's not trivial. But I'm not going to repeat those. Right? So there were these chain rule applied again and again and again. But there's nothing complicated here. This is just a variation. So does that make sense? So what I did for that sum at the beginning of the lecture, I can also do this for this integral. These are not independent because I have k constraints. So I can't say their coefficients are all 0. But what I can say is that I can choose an independent set of these, and I can make the coefficients of 0 by adjusting these. These are kind of free. These are just coefficients. I can choose them however I want. They have some physical meaning. As we have seen, they are related to force. But I choose these in such a way that the ones I left out, the not independent ones, I'm not going to call them dependent, but let's say not independent ones, have their coefficients 0, then this sum reduces to not from 1 to n, but from 1 to n minus k terms. And all the coefficients there has to be 0 because these are now independent. So this one must be 0 for all of them. It is 0 by my choice of lambda for the coordinates I left out. And then it is 0 for the independent ones because they're independent. But it's the same deal. And that one that looks very much like the Lagrange equation of the second kind is, of course, the Lagrange equation of the first kind. The book is using a slightly different notation. They're using something else here. I'll put it this way. There's a graph here. Okay, so let's take a 10-minute break, and we're going to take this and solve some problems. Now, there are some examples. So the book has some solutions of examples, but there are some typos and things like that. So if you have questions about those, like for example, this derivation. So let me just take 5 minutes. We have 5 minutes anyway. So this derivation is around equation 220, and in equation 220, there are around equation 220, there are some typos, like alpha turns into a, and yeah, there is some zeros disappearing or appearing. Yeah, so if something looks funny there around there, it is really a typo. There are a number of typos in those around those equations. Right? There could be typos here, of course, as well. But if you let me know of these typos, if something is funny here, I can fix that. But with the book, it's a little bit harder. So if you write those on perusal, then I can try to, address those. Typically, I don't get involved in the discussion of the perusal, but like a typo, of course, it's so misleading that I'll be able to fix it. Okay. So let's take it then.